Welcome to our first lecture where we really start speaking about magnonics. So before we have refreshed our knowledge about basics of magnetism, why some materials are magnetic, because spin wave can propagate only in magnetic material. And finally, in this lecture, we will discuss magnetization, precession, and Ladau-Lifshitz-Gilbert equation. So in this course, this lecture, we will discuss precession, Polder susceptibility tensor, LLG. Then we will go to very important part, Kittel equation, and we'll discuss so-called shape anisotropy. And then very briefly, we will discuss magnetocrystalline anisotropy, which is coming from the crystallographic structure of your material. What is magnetization precession? So in principle, these slides you have seen already in the promo lecture. You have lecture 0, which is uploaded, where in the simplest words we explained what is mechanical precession, what is magnetization precession. Therefore, I don't want to spend too much of your time on giving the same material. I will just quickly refresh what is we discussed last time. That as soon as you have such disk which rotates around this axis, then it will have angular momentum, which is defined like this R cross product P, where P is a linear momentum. And if you will try to get, in the simplest case, derivation of this, of the variation in time of this angular momentum dl over dt, then you can quite simply, with this simplest mathematics, show that it will be equal to torque, which is R cross product F. And that's the formula which we need in order to derive Ladau-Lifshitz-Gilbert equation. And this mechanical precession means that if your precession top is trying to fall down, force mg is trying to pull it down. Instead, it will create a torque, and we will get mechanical precession. Good. All this is known also from mechanics. And then we made the step from mechanics down to atomic scale. So we discussed Bohr model of electron. An electron is of atom, where electron is rotating around atom. He has positively charged nuclear. This electron has angular momentum, orbital angular momentum, LE, like exactly in the previous case, because electron has non-zero non-zero mass. But besides, electron has a spin, quantum mechanical thing, and this is also angular momentum, and we need to take into account J, total angular momentum. As soon as you have charged particle moving, then your total angular momentum will be coupled to magnetic moment, mu, via the simplest ferromagnetic ratio, gamma, which is shown here, which is just a fundamental constant, depending on Landau factor, charge of electron, and mass of electron. Then what we did, we made a step from the magnetization mu to from magnetic moment mu, which is used to describe magnetic moment of a single electron or atom, to magnetization. And for this, we multiply it with n, where n is not a number, but a density. So we need just to summarize all magnetic moments and normalize them by the volume of your material. Then we work with magnetization. And last ingredient we need in order to derive Ladau-Lifshitz equation is torque. So now we don't have torque created by mg force, but instead we have a torque which created by the field B, or magnetic induction B, which acts on the magnetic moment mu. And you can rewrite it again in terms of magnetization, and when you do all the simplest mathematics, you will get Ladau-Lifshitz torque equation, which shows that dm over dt, so change of magnetization in time, shown here, can be found as minus gamma m cross product B. Again, this very nice animations from Rostislav Sirga. So as soon as there is angle between M and B, field is trying to pull magnetization vector back to along, that it points along B, but it's not here. Therefore, what we have torque pointing in that direction. And as a result, we will get magnetization precession in this form. And that's what is shown here. So what you see here is I use two systems of units SI. So here it's defined through B effective, but in CGS usually it's written through H effective, like it's shown here. Good. Sorry. Now the question is damping. As long as magnetization precession is excited, it cannot exist forever. It will give its energy to temperature at the end of a day through spin-orbit interaction we will discuss later. But important is that it will stop existing after some time. So then dynamic looks like it is shown in this animation. Apologize. So let us wait for the animation. And this spiral behavior, like it's shown here, is described by the additional damping term. They are different, but in this case we show so-called Gilbert damping term, where alpha is a Gilbert damping parameter. What else is important here is that you see in the picture I have B0, it's magnetizing field, which we need in order to all magnetic moments are pointing in the same direction. But in reality, in the formulas I have effective field. So what usually people put into this effective field? It's magnetizing field. It's field describing dipole-dipolar interaction between spins. Field describing exchange interaction between fields. Anisotropy, if you have shape anisotropy, you can also put there, or if you have crystallographic anisotropy. If you have external exciting field, it also comes in there, or parametric pumping field, which is usually pointing along the B. It's all coming here, and then having all these components, we can describe even very complicated physics in our system. So that's an overview, it's clear. Now let us go a bit in depth in the LLG, Ladau-Lifshitz equation first. It has two fundamental properties. If you will take this equation and multiply it in scalar way with m, left part and right part, on the right part you have this vector is pointing in that direction, so it's always perpendicular to m. When you multiply it in scalar way with m, it will this scalar product will be equal to 0, like it's shown here. And on the left side, we will simply have dm squared over dt, so absolute value, like it's shown here. And this brings us to very simple but important conclusion that length of vector m will be constant in this Ladau-Lifshitz equation. So it means that here, this end of the arrow always draws sphere. If you will type Ladau-Lifshitz equation or Ladau-Lifshitz-Gilbert equation in Google, and will press show me pictures, you will see that, I don't know, 50% or so pictures will be wrong where this spiral is lying on the same plane. So it's not correct, it's not on the same plane. Length of m is always constant, so it always draws a sphere. I don't know, maybe not 50%, but you definitely will see some. Second fundamental property of Ladau-Lifshitz equation is direction of magnetization is constant. It always goes anti-clockwise. It's fixed by the charge of electron. And it's considered also as fundamental properties of magnetism because we always have one direction of precession. It kind of breaks in time inversion symmetry. Good. Yeah, so if you will look from the top, it's always anti-clockwise. Two properties of LLG, and now our job is to solve Ladau-Lifshitz-Gilbert equation. Ladau-Lifshitz. So far, we do not speak about damping. When somebody says LLG, Ladau-Lifshitz-Gilbert equation, Gilbert means that we already take into account damping. But at this moment, we still stick to the Ladau-Lifshitz equation. No damping at the moment. But we need to solve it. The easiest way to do it, if you want to get analytical solution, is to use an approximation of small amplitudes. That means that your biasing field, you split into two parts. H0, it's a static field, which we use to magnetize the sample. And in addition, you add another component, H with this tilde, which is dependent on time. Which means that this is external field which you use in order to excite your magnetization precession, H from tau. And it works, you can get analytical solution if you work in the assumption that this additional alternative component, H from T, is much smaller than the bias in magnetic field, H0. And another side, if you have alternative magnetic field, then you also will get magnetic component. It won't be anymore M0. There will be another component, which we also describe as M tilde, with as a function of time. And again, you work in the assumption that this M is much smaller than M0. What does it mean in practice? It means that angle of precession here is very small. And usually for spin wave business, this angle of precession is not more than 1 degree. So usually precession is very small. That's why we speak that magnets are interested for energy transport and processing, because you don't need a lot of energy to excite this magnetization precession, and then it can propagate itself. And for Ladau-Lifshitz-Gilbert equation, we also take into account that this time-dependent component is much smaller than M0. Afterwards, we do just simplest mathematics. We take Ladau-Lifshitz equation, we put this H, this M into this equation, and we will get the following equation. So dm0 over dt, dm small over dt, and here we will have 4 times cross product, m0 h0, m small h0, m0 h small, and m small h small. Now we need to simplify it, and this is easy to do, because M0, it's a static magnetization point in the direction of B0. It doesn't depend on time at all. There is no function of t. It means that dm over dt is equal 0. Simply, it's constant. M0 and H0, they point in the same direction. Therefore, cross product in between is equal to 0, like it's shown here. Now, what about this term? This one is very small, and h is very small compared to all other terms, yeah? As a result, when you take small variable, small parameter and make it square, it's getting a second order of smallest here, so we can ignore it. Therefore, we also take it out of our equation. As a result, neglecting all these parts, we are coming to this very simple equation where we already describe m small variable of the magnetization. So there is no M0 here. And now we need to solve this equation. To do that, we need ansatz. So we need to find a way how do we define particularly this external field. Yeah? So this magnetization in principle is given by the system itself. It comes from the physics of precession. But this external field is given by experimentator. So which field we want to apply. And in this case, usually what we do in experiments, we apply microwave field in some gigahertz frequency range, which creates then field H, which excites this magnetization precession. And microwave field, it means that this is simply simple oscillator, like harmonic oscillator, which can be described as e exponenta I omega t. Therefore, what we do, we use ansatz for field in this form, some amplitude e omega t, and then for magnetization, you also describe it in the same form, m e I omega t. Pay attention that omega is a circular magnetization, which is measured in radian per second or second into the power minus 1. Please do not mix it with frequency, which is measured in hertz. If you want to work with hertz, you need to operate with linear frequency f, which is omega divided by 2 pi, and this one is measured in hertz. Here are just formulas to make your life easier with how we search for cross product for this M cross product H 0 M0H, these two cross products. Yeah, and here I just show you the result, because what we need to do the next one, we need to take this equation, to use this ansatz, and to project it onto onto x, y, and z on Cartesian coordinate system. So we will get three equations. How is obtained? It's very easy. Yeah. So first you consider x-axis. You will get dmx. So you take only x mx coordinate over dt, and then you have this term. It's I omega is coming simply from the derivative from here. Yeah. This I omega is coming in front of your term. Second term, which is j, it will be then, of course, perpendicular to x, so therefore you will get here, because of this cross product, you will get here my, h0, and in the next case you will have hy. In the y projection to the y, you will get similar thing, and for projection to the third one, you will have 0. Why? Because our coordinate field, so you see that we take into account originally all three components of magnetization, mx, my, and mz, and hx, hy, and hz, three components for field. But for static components, we take into account that it exists only for the z-axis. Therefore, we have 0, 0, and h0. And the same for magnetization, 0, 0, and m0. As a result, if you will do the simplest mathematics, you will immediately see that mz component, this one, is also equal to 0. Then, having all this, mz is equal to 0, you have then consider only these two equations, so you have two variables, mx and my, and two equations. So it means you can solve that analytically, and you can get value for mx and for my as a function of hx applied and hy applied, like it's shown here. Here you will have such a bit bulky term, which depends on gamma, mu0, magnetization, omega h, so-called. Where is my omega h? It's here shown, okay. I will come in a minute to omega h, it's also simplification, and omega, our applied frequency, this one, omega. And the same for the same parameters for all of them, but principally they all stay in here. So what is omega h? Depending on SI system, it's gamma mu0 h0. And for CGS system, it's gamma h0, like it's shown here. Good. And then what you do in order not to carry such a bulky terms, you define two parameters. It's magnetic susceptibility, high, for this term, and high A. A stays for antisymmetric, is staying here. So you have high A, high, and minus I is outside. Because in this way, you can derive it all in the terms of Polder susceptibility tensor, that evolution of magnetization in Ladau-Lifshitz, given from Ladau-Lifshitz equation, will be given simply by susceptibility times H, applied magnetic field H. Susceptibility is tensor, it's named Polder tensor, H is applied magnetic field. And here how our Polder tensor looks like, where these are all the parameters. Here besides omega h, you have also omega m, and here's defined omega m in SI units of system and in the CGS system of units, like it's shown here. So principally this omega h is simply rewritten function dependent on the frequency, and omega m it's a frequency dependent on the magnetization m0. Please do not mix this high with high, which we discussed in the previous lecture, because that was static susceptibility. Yeah, so you had static material, you apply magnetic field, something is magnetized, and you see how your material reacts onto the static magnetization, on static magnetic field. And here you apply alternative, so it's AC susceptibility, it's alternative susceptibility, and it shows you how your material reacts onto the applied microwave field or applied alternative field. But the unit of the high is still the same, it's unitless. Yes?
Just before the slide, in the cross products, what is I, J, and K?
Coordinate vector, so which show in the direction where it goes and has a unit length. You didn't define it, you defined it differently in algebra or in some basic?
No, I was thinking there was probably both.
Okay. Principally, if you plan to do magnonics, I recommend you to do this mathematical routine once in your life to understand where it comes from. It's not very, it's quite easy. It won't take you much time, but to get Polder susceptibility tensor is always good because it's more or less the solution for the Ladau-Lifshitz equation. Other questions, more comments? No? Good. So, what does it mean this tensor? You see, we have here a very suspicious thing that omega h and minus omega square, because in this case we do not consider damping, and it means if your omega is equal to omega h, susceptibility tensor goes to infinity, plus infinity or minus infinity. So here is shown this two parts of susceptibility tensor, high and high antisymmetric, and asymmetric, and then this one solid line, and this is dash, and here it's shown as a function of frequency, because it's very important. In this magnonics business, you usually have two opportunities. Either you change frequency and see what happens in your system, or you change field, see what happens. If you change frequency, field is constant, but then in some point, the frequency, you will reach this value omega h. And when you reach omega h, then this tensor should go to infinity. And you see, if you are reaching omega h from the left side, it will be plus infinity. If you move from a high frequency down to smaller frequency, it goes to minus infinity. Good. Then we have the following situation. If you change now frequency is constant, let's say 7 gigahertz, and I don't change, but I can change field. So it means that I'm changing more or less omega h. In this case, you have some susceptibility, but when you come into the place gamma h0, you will have minus infinity susceptibility, and when you come from higher frequency down to smaller, it will be plus infinity. So again, our susceptibility tensor goes to infinity, and this is a signature of resonance. Yeah? So it means that here we have resonance, which is, we can say it already now, nothing else as ferromagnetic resonance. Another important part in conclusion from this at this point we can define gyrotropy. If you will have a look, or maybe it's easier not through tensor but simply through this formula, you see that mx depends on both fields hx and on hy, and my depends on hx and hy, which means that if you will apply a linearly polarized field, that it changes only in one direction, for example hx, or only hy, you won't excite only one component. If you apply hx, you won't excite only mx, because you also will apply my. So you will never excite magnetization precession like pendulum. It always will be precessing. And this is fundamental property, so there is a phase shift in between these two components pi over 2, and all this in general is named as phenomena of gyrotropy. Yeah? So magnetization precession by definition is gyrotropic. Yeah, and second is, so what we discussed, another peculiarity is that it's not symmetric, this tensor, you see? Here staying with minus I, and here's with plus I, and we see clearly the resonance dependence, that we will get resonance excited when we are coming to when we have correct field or correct frequency. And with the very last slide here, I would like to define permeability. There is another term, permeability, which is defined as mu. And permeability is a measure of magnetization that a material obtains in a response to an applied magnetic field. So it's how it reacts to the field. And it can be defined through the susceptibility principle. Yeah? So mu is equal 1 plus 4p high in a CGS system, and mu is equal mu0, 1 plus high in SI system. And then when you will just do simplest mathematics, we'll place everything into the formulas. You will get Polder tensor for permeability, mu, which also is defined like that and looks slightly different. These components mu and mu asymmetric shows different. If you will plot now mu as a function of field, or again as frequency, depending what you change in the system, you again will get more or less the same result, that you will get resonance at this value when it goes, permeability goes to minus infinity or plus infinity or minus infinity. With this, I am done for today. So we will continue, we will include losses next time, and we'll try to change our solution for Ladau-Lifshitz equation with taking into account loss, and we'll see what does it change in our physical system. Good morning, everyone. We continue our lecture 2, and today we discuss Ladau-Lifshitz-Gilbert equation with taking into account magnetic losses. Strictly speaking, this equation dm over dt minus gamma m cross product b is not really Ladau-Lifshitz equation. It was very simple, and it comes directly more or less from mechanics. The proper Ladau-Lifshitz equation, you need here this another term, which is R, which means that you need to take into account damping term in your equation. So then this is a proper Ladau-Lifshitz equation. And this damping term, as we have seen already in the starting lecture, describes us as a physics that after we excited magnetization precession, there will be no precession after some time. So it describes this motion like spiral. There are different ways how you can describe this term R, damping term. One of them is originally written by Landau and Lifshitz, and here you have it's written as M cross product H effective. And here there is parameter lambda, which describes the damping, how strong damping is in your system, and it's all normalized by ms squared and so on. There is another much more commonly used approach. It's named Hilbert damping, and it's written in such form: M cross product dm over dt. And this alpha, it's a Gilbert damping parameter. It's a very important parameter for Magnonics. One of the key issues, we always start with alpha if you want to decide if this material is suitable or not for spin waves. And that's how it's written, and it's principally empirical formula, but very popular, so that's how people do it. But if you will do simplest mathematical substitution, you will replace, instead of lambda, you will put alpha m and this part, and instead of gamma, you will put gamma normalized by 1 plus alpha squared. If you will plug everything into Landau-Lifshitz form, you will end up with a Gilbert form. So it means that physically that's practically the same. Just question how it is written. Important is that there are other terms, and very commonly used in paramagnetic materials, but in particular is Bloch-Blombergen form. And this one gives us very different physics, because Bloch-Blombergen doesn't save the length of M. So precession then end of this arrow doesn't draw sphere, but it has some another more complicated shape. So there are different ways how it can be Bloch-Bergen form can be written, but the most commonly used is T1 and T2. So people in quantum physics intensively using it and so on. We don't have, so there are simply different damping mechanisms. Some are described by Gilbert, some are described by Bloch-Bergen, and it also depends with which material you're working. So here, like phase relaxation is important and so on. So we don't go for it, but just for you that you are aware that there are different ways. In this lecture course, we will stick to Gilbert. What is Gilbert damping term? So principally it describes nothing else as viscous damping. Viscous damping, the best example we have when we are driving a car. Here I just have found some graph made for Volkswagen Golf. And what it shows us benzene consumption, fuel consumption as a function of temperature, of speed for different gears. And you can clearly see that if you drive 80 kilometers per hour on this gear, you will consume 4.5 liters for this machine, for this particular type of car. But if you drive 180, you will spend like 12 liters, so 3 times more, almost. And the reason for this is very simple, that when we go very fast, the resistance from wind is large, and then we have to pay with extra fuel. And Gilbert damping explains exactly the same. If your precession is very fast, your frequency of precession is fast, the oscillations will die fast. If it's slow, then magnons live long time. So precession is longer living. In order just that we are memorizing better what is viscous damping, there is this fun video how they are using this phenomena in liquids in order to stabilize houses, buildings.
Inside a pressurized cylinder with fluid that travels between 2 internal chambers. This works similar to how shock absorbers on your car operate. As a building moves during an earthquake, the damper piston forces fluid from chamber to chamber, converting the dynamic energy into heat energy, which is absorbed and dissipated by the damper itself. The effects of an earthquake on a building with and without dampers
See how now it keeps
the
building.
transference of energy through the damper fluid minimizes lateral movement and stress on the structure, which can lead to collapse. Dampers are configured in a variety of ways to accommodate different.
Okay, these are details, but this is a nice
shapes.
example where we use viscous damping in our everyday life. Another, let's have a look. Again, it's mini lecture about different type of oscillations with different classification depending how strong damping is.
The loss of energy in an oscillator is called damping. In this video, we will be specifically focusing on damping in a spring and mass system. Damping can occur within the spring due to energy loss from internal stress and as a result of external drag from air or water. The damping in an oscillator can be described in 4 ways: undamped, underdamped, critically damped, and overdamped. In order to analyze these categories, we can use the experimental values beta and omega. Omega, the angular frequency, is equal to 2 pi over the oscillatory period. 2 beta is equal to B over M, where B is the decay constant and M is the mass of the system. The decay constant is found by fitting the peaks of oscillation to an exponential curve. If beta is 0, the system is undamped. Perfect undamped motion is impossible to achieve with a spring and mass system in the real world. Over a short period of time, however, the decay from air friction is negligible enough that a spring and mass in air can be representative of an undamped oscillator. If beta is less than omega, the system is underdamped. In an underdamped system, the amplitude of each oscillation gradually decreases until the amplitude reaches 0.
This will be our case.
If beta is greater than omega, the system is overdamped. In overdamped systems, the system returns to equilibrium without ever oscillating. If beta is equal to omega, the system is critically damped. For critically damped systems, the system returns to equilibrium without oscillating as quickly as possible. This is similar to overdamped oscillatory motion, but it returns to equilibrium more swiftly.
Very nice demonstrator. What kind of damping we can have. So now, what is the motivation behind the next slides, which I'm going to present to you? The point is that there are many different ways and parameters and variables which we use to describe damping in the system. And I decided to devote 10 minutes or so and to go through them that you can a bit sort it, you can sort it for yourself. And here I would like just to start with repetition, which we probably have in the course of oscillations and waves, maybe, in mechanics. And here we just briefly describe the oscillator with a damping. So we have such spring, there is mg force, which is pulling it down. Principally more correct, it would be to put it in horizontal position and assume that friction force is zero. But if you use the 0 point in the coordinate x as a steady state, when mg is already compensated with Hooke's law here, then you can show mathematically that at the end of the day you will get the same equations. And what forces we need to take into account? Friction force, and this is our viscous damping, because you see that it's proportional. So here there is tan h, which is some proportionality constant, which shows how large is your damping. It's our alpha more or less, proportional to our alpha, and times velocity. So the stronger, the larger, the faster speeds, the larger is force, friction force. But when you write second Newton law, so you know all the definitions here, x with point means dx over dt, it's velocity, first derivative, and acceleration, x with 2 points, dv over dt. And then on the right side, we need to write force according to the second Newton's law, and here we have friction force, but also Hooke's force, yeah, so d times x, which means that force of the spring is proportional to the displacement, and d is just a Hooke's constant factor characterizing the spring. Okay, so all this you know very well, and when you will plug everything in, you will get this equation, which you also probably have seen many times. It's standard equation for any oscillator with damping. So it's always written in the way that there is second derivative, and you can rewrite it omega 0 square x, and here staying 2 delta x point, which describes, this term describes the damping. If you will now compare these two equations, yeah, so this one is written for concretely this case, and this one is a general form, so you can immediately define damping parameter delta, which will be proportional to h, means the stronger viscosity, the larger damping is, but inversely proportional to mass. So it means that if you have very heavy oscillator, damping is not so pronounced, it's hard to stop it. And on the right side, there is omega 0 squared, which is in this case is simply d omega m, so it's resonance frequency squared, and d is our Hooke's constant, so it means that if you have very strong spring, oscillation frequency will be large, or if you take very light body. If you have heavy body, frequency drops down, so oscillations will drop down. Good. How to solve it? This one. So for this, there is this approach of slow amplitudes is used. Strictly speaking, if you want to find analytical solution, you need to use the slow amplitudes. It means the following, that variation of the amplitude of your precession is not constant of your oscillations. It depends on time. But what you assume here, that this dependence of time, x a over t, is much slower compared to oscillations themselves, e omega t. Yeah, so these oscillations are fast, but variation of amplitude can be slower. Only in this case, you can use this approach and you can get the solution. And in mathematical, it means that you principally assume that omega 0 a is much larger than omega 0 a point, much larger than a 2 points. Also, please pay attention to this CC, which means complex conjugated, because we usually, when we want to describe oscillations, we write just exponenta. And that's it. But exponenta is cosine plus E sine. And strictly speaking, it's not correct. A correct answer for harmonic oscillator, it would be cosine, simply. And that means that the correct answer, so like mathematically correct, would be this part plus complex conjugated, which means that A minus I sinus, and then sinus simply disappears, and you will stay here with 2A cosine, and this will be the correct answer. Therefore, in only in these slides, I will carry the CC just to for these formal reasons. Having all this assumption, what you do, you just search for derivative, and that's the easiest mathematics, which we do. It's derivative from this first component times exponenta plus a derivative from exponenta, so this E omega 0 comes here, A simply stays as it is. Then you do the same for the second derivative, you will get second derivative from A, you will have here first derivative from A 2 times, and then you will have the situation when you took 2 times derivative from this exponenta, and then you will get minus omega 0 squared A, minus because I squared will give you minus. So simplest mathematics, and what you do afterwards, you just plug everything into this equation, and as a result, then some terms, this one will simply disappear, it will be, it's the same term with different sign, minus and plus. This term we remove because we are working in the assumption of that our damping is small compared to omega 0. So it means delta is smaller than omega 0. It means that we have small damping. There is damping, but it's small. Therefore, delta is, therefore this term is simply small compared to this one, for example. Therefore that one also disappears, and you will get this simplified equation, which can be rewritten in something very simple, like this one. A point plus delta, damping parameter A equals 0, which you can easily integrate and solve the differential equation. And then, of course, there will be some constant, but we just introduce that as a 0 time point. The amplitude of oscillator was A0. Just rewrite this constant. And then we will get the following simplest equation, which you have seen many times already, to get damping A equal A0 E to the power minus delta T. What is the total solution? But this is solution only for A, yeah? Only for the variation in time. The total solution of your equation, you need to come back to the equation solution for the oscillator without damping, which is simply cosine, or this 2 exponenta. And then x from t, so this coordinate is a function of t changes as this exponenta plus complex conjugated times e minus delta t. And if A0 is real, because it can be also complex, but if it's real, then you can replace it with cosine, as we discussed already. So this is the most classical, the most simplest, and probably the most correct way how you describe simple harmonic oscillator with small damping. What the physical meaning is, the same which you have seen in this little video. It means that amplitude decreases exponentially. And here there are 2 main parameters are important. So first of all, it's periodicity, T0, which is more or less this period. And you can find it 2 pi over omega, where omega is a circular frequency. And second parameter is, of course, lifetime. Lifetime tau, it's a time during which amplitude of your oscillator. Please do not mix up with intensity, because in experiment pretty often we measure intensity in majority cases, and intensity, it means that you need everything should be squared. So intensity is amplitude squared. But then lifetime will be different. Majority of the cases, lifetime is defined particularly for amplitude. And then when amplitude decreases from its maximal value down to 1 over E, so 0.37, this is our lifetime. Yeah, and of course you understand this very well, but if I say that we will have 1000 of precession periods of magnetization. I refer to this point when amplitude of precession drops down. So of course, we still have a long time we have precession, but we need to characterize the system, and for this we just use tau lifetime. Good. So then we have already delta as a damping parameter, yeah, which simply stays in this equation, 2 delta here. We have tau. What else we can have? Very physical and often used relaxation frequency. It's omega r. R stays for relaxation, and it's simply 1 over tau. Again, please do not mix up with f. Yeah, so here should stay not linear frequency, which we measure in hertz, but here should stay circular frequency, which we measure in 2 pi f. Yeah, so it's 1 over second. It's or radian per second. It's a unit. Another, pretty often people write that omega r relaxation frequency is an imaginary part of omega. This is also used everywhere, important to keep in mind. And you can easily show if you just replace your omega with omega prime plus omega I 2 primes, I omega 2 primes, you will plug it into the simple exponenta, you will immediately end up with a standard formula where you have omega prime is our omega 0 before, and omega 2 prime is our omega relaxation. Therefore, always keep in mind that as long as you have a complex frequency, it means that there is damping somewhere in your system. And in the case of Gilbert damping, we can couple tau, this lifetime, with the Gilbert damping term alpha, and tau is simply 1 over alpha omega in the simplest case. In reality, in experiments, there is also some offset pretty often here. Therefore, one need to be a bit more careful. We will discuss with it, and we'll discuss FMR. But in classical case, this line should go to 0, because if frequency is 0, there is no damping, no motion, no damping. Therefore, it should go to 0, and this angle more or less is our alpha. And yeah, and here we can finally explain why I said that inverted alpha gives us the number of periods. So if you take tau is as lifetime as t0 divided by 2 pi alpha, so more or less I just take this omega and replace it with 2 pi over t0 here. Then if I take tau lifetime and normalize it on the number of periods, on the duration of one period, on t0, then I will have here 1 over 2 pi f alpha. Oops, f is not here, sorry. It's misprint. F is not there, it's already in t0, but 2 pi over alpha. So it means that this ratio is more or less proportional 1 to the alpha. That's what I said, that we will have alpha, it does not depend on the frequency. So it means that if your alpha has, it's, let's say for simplicity, 10 to the power minus 3, it means that there will be around 1000 periods before your amplitude goes to 1 over e, more or less, with accuracy to some little constant. And but the time which it will take for this precession depends really on the frequency. So if it will be 1 gigahertz for precession frequency, then 1000 period means that you will spend 1000 nanoseconds. So lifetime will be 1 microsecond. If you increase frequency 10 times, your precession frequency is 10 gigahertz. As we know already from viscous damping, the lifetime will be 10 times smaller, and this will be only 100 nanoseconds. So there will be lifetime will be smaller. That's why, depending on what kind of experiment you want to perform with spin waves, you need to keep in mind that lifetime strongly depends on frequency, and alpha is parameter for material. So yeah, and here I just bring you back to this table where we discuss different kind of samples and different type of materials which are commonly used in magnonics, YIG, yttrium iron garden, permalloy, cobalt iron boron, Heusel, and so on. Here's alpha, And you see that for thick YIG, it can be of a single crystal without substrate. For sphere, for example, it can be 10 to the power minus 5. For thin YIG, it's 10 to the power minus 4. And for metals, it's 10 to the power minus 3. And then the lifetime is going to be, for YIG, it can be hundreds nanoseconds. For thin YIG, it will be a bit more than 100. And several nanoseconds for metals. Please pay attention. You see here at the bottom the retained frequency, because as I said, it's inversely proportional to frequency, therefore important to show always at which frequency. And these frequencies were selected simply because we apply 100 millitesla static field to all of these materials. So we fixed here in the stable field, then depending on magnetization, frequency is defined. For metal, saturation is larger, therefore frequency is larger. And then at the end of the day, we will get a damping lifetime. And for YIG, saturation magnetization is smaller, therefore the frequency is smaller, and this gives kind of additional contribution 2 times to the lifetime. But principally up to 1 microsecond lifetime you can achieve in YIG sphere, for example. Which is very critical, by the way, for quantum. So if you want to, quantum magnonics, if you want to couple your magnon to qubit, so let's say with a typical coherence time 1 microsecond, then you want magnon to live the same time. So you need also 1 microsecond for that your magnon lives. Therefore, YIG sphere is now the most popular object in terms of quantum magnonics. Yes?
So just according to these stats, why would you use nanometer-thick YIG? Because like the stats you wrote down, they are pretty much better in every way for micrometer-thick YIG, right?
Thank you for the question. So I repeat it. Why do we need a tall nanometer thick if we have thicker and better micron thick? Yeah? The reason is the following. Magnonics, it's one of the main advantages in terms of processing data is scalability. We can go to very small wavelengths and very small sizes. But if you have sample of 5 microns thick, you cannot reach 50 nanometers. Simply technology, there is no technology, or there will be some huge pillar. And therefore, if you want to have 50 nanometer, we also went down to thickness at 30, 40 nanometers, and it's possible. Simply scalability, but then, of course, ideally would be to do quantum magnonics with this property on this scale, and it's kind of win-win. Good. Other more questions? Yes?
What is the main mechanism for nanometer thick YIG that the damping increases?
That's because of interface. So it's growing the best. There are no. Yes. Yeah, so I repeat the question. What is the reason, physical mechanism, the damping for nano YIG is increased and as for thick YIG or bulk YIG? The reason is following. It's growing procedure. So nowadays there are several different ways how people grow such nanometer thin YIG, but the most commonly used is pulse laser deposition and liquid phase epitaxy. Liquid phase epitaxy is a very old classical technique. That's how this sample is done. But when you grow it, how it works, you take this melt, there is some platinum crucible in which you have a chemical, I think 1000 Celsius temperature, if I remember right. And then you put gallium gadolinium garnet substrate and you put it in and you rotate, and then you measure how long it grows, and then you take it out, cool down in the evaporation. So it's very, very complicated technology, but also very old. That's why it's so well developed. And the problem is that when you start doing it, gadolinium ions from substrate, there is a mixture. They are going to YIG, and also this interface just between YIG and GGG is not very clean. So there are maybe different contaminations and something else. Therefore, the interlay between YIG and GGG is an issue. But if you have 5 micron thick YIG, which is pure YIG, and only, I don't know, 50 nanometer is unpure, then usually you can ignore it. It's not so important. But then when you go to 50 nanometers, then it's a problem. So that's one reason. Another reason that this magnon damping, it's usually coming, also there is also 2 magnon scattering mechanisms which are taking place in the inside of the sample on some impurities, inhomogeneities, defects in crystal structure, so, but also on the surface. Bottom surface on GGG and top surface. And then, of course, volume ratio surface to volume matters. So if you have very big sample and surface, just 2 of them, they don't play so much role. But when your surface is already, so let's say volume to surface is getting very small, this ratio, then surface also scattering, the surface is getting important. But people are trying hard to decrease this value, and principally this material is rather new. I think over the last 5 or 10 years, maybe 5 years, people learned how to grow it. So we using YIG from Carsten Dubs from Innovent. It's one of the best YIG in Vienna, our long-standing collaborator, and we are very happy. And he managed to grow, to bring thickness down to 8 nanometers or so, I think, with liquid phase epitaxy. Yeah. No more questions? Okay. Good. Last question. Imagine that you measure ferromagnetic resonance or any other resonance, and you know how do we usually define damping. We have some resonance curve, which is usually described by Lorentz, and then the width of this line gives us damping. Why is that? Then we operate in terms, for example, full width, half maximum, this one. Why is that? You can easily understand if you will simply take this function. So here's the precession term, there's I, yes, so this is just oscillation, and here is your exponential damping minus I AT, if you can see it. But then you just take Fourier transformation and you will get something like that. This term I just took it from this lecture notes from Stanford about Fourier transformation, but that's something you can do yourself also easily. And then what you will do afterwards, usually you want to deal with power spectrums. That's what is also measured in experiment, which means that you need to take this Fourier transformation and to square it. And when you do it, you will get here A squared for P squared S squared. So this part is more or less responsible for the frequency, and A is your damping. So this is Lorentz function, and you can immediately see that this A squared is equal to this minus AT. Because this one we know already, it's omega R, it's a relaxation frequency. So it means that full width, so that's what you need to know, that if you defined your evolution in time with omega R, then in Lorentz, here stay in omega R squared. So they are coupled, one with another. And if you want to speak about full width half maximum, don't forget about 2. So pretty often people, even scientists, active scientists, making mistakes. So be always careful with 2 and with that which damping parameter you are using. In experiment, pretty often people also use derivative when they measure not this curve, but they measure derivative, dA over d omega. And then you need, it's even more complicated. You need to get some additional factor, I forgot, something, either square root of 2 or something like this additionally, to be able to define everything. Therefore, my message is very simple: be careful with these formalities. So much about different damping parameters. Other questions to this part? David has a question, I see.
Yes, I have a question. The damping parameter should be unitless, no?
If damping parameter should be unitless, depending which one. If you speak about alpha, alpha is unitless, tau is seconds, like any time, omega is 1 over second.
And delta?
And delta, so it looks like it's the same as omega r. relaxation frequency. So it should be.
Beta and alpha are different.
Yes.
Well, we also said beta is a damping.
Let's have a look on this equation. So here you see that delta has the same unit as omega, because x gives you one d over dt, yeah, one frequency, and then another one. So, and you said that they are.
So that we call it damping parameter before. So,
Yes, it is damping parameter, but that's why we need always to pay attention with which damping parameter we are working. Good. Okay, so then, I forgot this part. It's especially done for quantum physicists and for people who get used to work with microwave engineering and so on. They are strongly coupled alpha and Q. So principally Q factor. So if you take a resonator, you always can reach some Q factor, which is F over delta F more or less. Is 2, and alpha it's nothing else as, so Q is equal 1 over 2A, and alpha is, so that means that alpha is inversely proportional to the Q factor, which you can achieve. And again, coming back to these equations, we will have clear understanding that if you want to have Q larger than 1000, then you need to work with pure EEC. You won't be able to get such high Q factors for other materials. Good. Coming back to Polder susceptibility tensor. We have solved already Ladau-Lifshitz equation without taking into account any damping. So now we want to take into account damping, and the easiest way you can do it, knowing all this what we just discussed, when you take resonance frequency in your Polder tensor omega h, and you replace it with omega h plus I alpha omega. So you simply artificially can add this term damping here. So it's complex part, yes, as we discussed. Damping is a complex imaginary part of frequency. Therefore, it's imaginary here. And then having all this just plugged in into the equations which you have already, just by formally, you will obtain susceptibility tensor high with taking into account damping. So there will be again high prime, but in addition there will be complex part high 2 primes, which describes damping, and for antisymmetric part there will be also high prime and high 2 primes. And then there are many formulas there, so they are bulky. And moreover, you see there is staying this 1 over d. You remember that there was ratio, and this what stays at the bottom is this large part describing, again, it's more or less, it looks slightly different than Lorentz, but it's very close to Lorentz curve, because this is a part which describes damping. And you see that it depends on alpha and omega h, which is more or less our resonance frequency, but also, this part. That's a point where you define resonance, and you see that here, if you would be just Lorentz, there would be no this part 1 plus alpha squared, and our alpha is very small. If it's, for example, 10 to the power minus 4. Then it means here we have 10 to the power minus 8. It's very, very small compared to 1. Therefore, this part, strictly speaking, can be ignored. So alpha can be ignored. And then you're coming back to normal Lorentz. But on another hand side, if you want to work with material which has large damping, then keep in mind that damping can shift your resonance frequency of your oscillator. It's also something very well known from basic oscillations and waves. Usually people forget about it, but there is a dependence of resonance frequency on the damping. but very weak one, and for very large dampings in your system. Good. What does it bring us physically now? Introduction of the damping. You remember that high in the previous case when we were coming to the resonance field like this one, it was going to infinity, which is absolutely unphysical because we cannot get infinite susceptibility. Now, with taking into account the damping, you see that there is resonance, like Lorentzian resonance, symmetric, or there's this antisymmetric part for high prime, and for imaginary part high 2 prime, it's just more or less Lorentz. And that's how it looks for high, and that's how it looks for high A. And for us, it's very important that this is clear classical resonance, shown here. And now, and if we do ferromagnetic resonance, principally what we do, we measure these high 2 primes via absorption of microwave power, but this will be discussed later. But important is that when you have measured this high 2 primes, then you can define resonance field, resonance frequency, and then you know magnetization, for example, in your system and so on. And width of this peak gives you alpha, gives us damping. And that's how it works in practice, how we are characterizing magnetic materials. Good. Other questions to this part? No? All is good. So we've got resonance, and now we are switching to Kittel equations. Why? Because what we discussed before, there was no principally coordinate. We assumed that our material is infinite in space. And it was logical to start with it, but when you want to perform experiment, you need sample in some form. And if you want to come to real size of real sample, you need to take into account so-called shape anisotropy or demagnetization. So to explain the magnetization, I would like to start with the simplest case of if you take dielectric and you apply electric field into this dielectric. As we all know from electrodynamics, which we studied, there will be small displacement of charge inside of dielectric in a way that this displacement will create a new field which is trying to compensate applied electric field inside of your sample. And this is very typical for nature. It's always trying to minimize energy, and for this, pretty often you apply a field which is also the response of your system is going in a way to compensate or to minimize external field or external perturbation. What happens if you take now magnetic sample and instead of applying electric field, we apply magnetic field? In this case, physics will be very simple. There will be formation of some people pretty often speak about kind of imaginary monopoles, magnetic monopoles here. Also, we know that there is no monopole. Yeah, if you have magnet, if you cut it into two, there will be again there will be magnetic dipole from both cases. But here one can describe it a bit in terms of magnetic monopoles. But the idea is that there will be formation of internal field pointing in the direction opposite to B0. So it means that your magnetic sample will try to minimize magnetic field inside, and field inside your sample will be smaller than field outside, than the field which you applied. And then how you can find this internal field? Usually it's just B0, which is external. Sometimes people write external, or simply B0, or field in magnetic induction, B, you have to be more correct, plus BD, which points in the opposite direction, but here are vectors. So that's the first message, that there is the magnetization, there is decrease in the field in your sample. But there is another very important point, which we should never forget, is that if you take sample of arbitrary form and you apply a magnetic field, field inside sample won't be uniform. So in the middle it will be different at the edge and the corner. And this makes our life very interesting when we want to describe real nanowaveguides with complex shape. But here we need to go from the basics, and basics says that there is one form when field will be uniform, and this is ellipsoid of rotation. So if your sample has this shape, then your internal field will be uniform. So it will be the same any point. It will be smaller than external field, but it will be the same. So from magnetostatics, we can use this simple equation that this Dirac field can be rewritten in the following form. So here mu0 is just to switch more or less to, from field H to B. And then N, which is demagnetization tensor. Here it's written in a general case, and XX, YY, ZZ, and all other components. It's the first step. And this demagnetization tensor should be multiplied with magnetization of your sample M, because magnetization is defining how large is your Dirac field will be. In relative, what we usually do, we apply this field B external, or B0, along one of the axes, X, Y, or Z of the ellipsoid. And in this case, you can diagonalize this matrix and X and Y and Z, or sometimes people write X, X, Y, Y, Z, still. And this is a practical case which we consider in majority of the experiments we are performing. And one very helpful and very general property of this tensor is that the sum of these three components of the tensor is constant. If you do it in SI, it's simply nix plus ny and z are equal 1. If you do it in CGS, there will be 4 pi. That's very important because it helps you to understand how strong is the magnetization is in your concrete case. So let us write our equation. So we forget about damping again. At this point, let us focus on the resonance frequency itself. And we will have now this equation. And what we do, instead of B effective, we put not only B0, but we put the demagnetization term Nm. And we again use approximation of small amplitude. So it means that magnetization M again is split it into a static component along Z axis M0 plus dynamic component M0, M small 0. And B and M0 are parallel to Z. Okay, if you take this, then you need to do the same mathematical routine which we did already when we performed, when we obtained tensor, Polder tensor. You just need to plug everything in to split into x, y, and z components so that I don't write it. Still mz equals 0. And then having all this, you will get equation with 2 variables, mx and my, and 2 equations. So it means that you can solve that, or you just take determinant and make it equal to 0. And in this case, you can find immediately from the system of equations, you will get the answer for the resonance frequency of your sample. So omega 0 square, omega h, and such term. As you remember, in previous case, when there was no shape, when we were working with material unlimited more or less, the resonance frequency was omega h, simply this one, and it was simply gamma b0. Now, when we have sample, real sample, and with some magnetization, with some shape, and with some size, the resonance frequency has changed. And now it depends not only on omega h, which depends on field, but it also depends on the demagnetization tensors, and x and y and xy. The last what you can do here, you can so principally here is a still general term because here we have x and y, But if you will now orient B0 along one of the axes, then you will get famous Kittel formula. So this is a formula which describes the ferromagnetic resonance frequency of a real sample B0, and you see that here there is the magnetization XY and as X, Z, Y, Z, and so on. We will play now a bit with this formula. Here again, I give you two versions in SI system of units and in CGS that you can select that one which you like to work with. There is one more assumption which we took here, I forgot to mention. So there are two assumptions. It works for ellipsoid of rotation. And second, this ellipsoid should be small compared to electromagnetic wave. Because electromagnetic wave, if it's 10 gigahertz, it's 3 centimeters, yeah, so your sample should be smaller. And then it works. If your sample is big, that you have already different phases of electromagnetic waves, and you cannot use it. And principally, this Kittel formula describes nothing else as ferromagnetic resonance, which is coupling between an electromagnetic wave and magnetization of a medium through which it passes. This coupling induces a significant loss of power of the wave. The power is absorbed by the precession magnetization, or more precession, yeah, of the material and lost as heat. So it means the following, that more or less this formula is used in real experiments to analyze ferromagnetic resonance dependencies or measurements. Other questions to Kittel formula? Okay. Now let us play a bit with it. Why it's important? In reality, we don't use often ellipsoid of rotation, but it's a very nice analytical formula which allows us to come from it to real cases and of thin films of a cylinder and a sphere. So sphere, it's easy. It is ellipsoid of rotation by definition, just it's symmetric. But if you take your ellipsoid and you press it down in a way that this lateral sizes are infinitely large, that's how we usually describe thin films, infinitely large, and of some finite thickness, then it's still you can use formula for ellipsoid. And that's how we describe our thin films, because we usually work with thin films. The same with cylinder. If you take ellipsoid and stretch it to infinitely long, you still can use the same formulas. And here is written the magnetization tensors for different cases of thin film or thin plate, cylinder and sphere. And how to define it. So these parameters you can principally define on your own without knowing them, because we have this very simple formula that the sum is equal, it's constant. And if you go to sphere, for example, it is symmetric. It means that if you want to magnetize sphere from this, or from this side, everything is the same. It means that these three terms should be the same, and X and Y and Z, and you immediately can say what is a demagnetizing term for sphere. It will be 1/3 for in SI or 4π/3 in CGS. How to deal if you are working now with thin film like that? Field B0 is applied along Z, and we have this situation. So we need to find out what is N for this direction, for this, and for this. And here you do it very easy. So if you want to use approximation for ellipsoid of rotation, I said that this size should be infinitely long. Demagnetization, I said that you can think of it in terms of magnetic monopoles, but now which create field that compensates this one. But now your monopoles are shifted infinitely far away. So it's in this direction, you magnetize it like that, and these monopoles are infinitely far away. It means that field which they create is at the point of center of your sample, let's say, is 0. So that means that if you have thin film and you magnetize it along in plane, you can ignore demagnetization. There is no demagnetization. Field inside will be the same as field applied. And that's And then immediately you can say that nz in this case will be infinite, will be 0. And if you know that nz is 0, now let's see what will be nx in this case. Again, thin film, infinitely large, and x also will be 0. And then having an understanding that the sum of 3 Dirac tensors is equal constant, you can immediately say that ny will be 1. Or 4 pi in CGS. And let's have a look what we have here. Tangentially magnetized here, and x equals 0, and z equals 0, and y equals pi. If you do the same for cylinder, then nz will be 0, and x and ny are equal. Then you will have 2 pi, 2 pi. This table is written in CGS. Yeah? So Milko and Gurevich, they were working with CGS. And and if you work with sphere, then it's simply f4 pi over 3, 4 pi over 3. So this is the formula. You can find everything in the book. And here I just want to spend 5 minutes and to show you, to bring it all to the practice, to explain you how it changes the resonance frequency. Because we take the same material, but different samples, or we magnetize the same sample in a different way, and let's see what is the frequency of ferromagnetic resonance. So we take yttrium iron garnet, this material which we like. It's saturation magnetization in CGS for pi m0 1750 Gauss. I take ferromagnetic ratio gamma, especially in this divided by 2 pi. When we measure it, simply 2.8 megahertz per Ørsted. That's how people usually work if you want quickly to estimate what will be the frequency. And we apply 2 kilo-Ørsted field. 0.2 Tesla, sorry, M is mistake here. So let's consider thin film, and we apply field in plane, and Z and is x equals 0, this is 4 pi. We just plug everything in the formula, and we will get this very simple version for the formula, and we will see this F perpendicular or omega perpendicular often, because this is the denotion for the tangentially magnetized thin film, for ferromagnetic resonance in tangentially magnetized thin film, omega perpendicular. And if you will simply plug everything in, you will get that frequency will be around 8 gigahertz for the applied field of 2 kilo-Ørsted. Okay. Yeah?
Is that a mistake? I think if you have 2000 Ørsted, you should have 0.2 Tesla.
Yeah, that's what I said. This is a misprint. It's 0.2 Tesla. Yeah, the scaling factor is 10 to the power 4. And I will fix slides for you, but for YouTube readers, it will be already like it is. And now we take the same take the same sample, but apply field not in plane but perpendicularly. And again, so in this case, an x is equal 0 and y is equal 0, and all the magnetization goes to the z direction, like it's shown here, and your frequency will be, so you see here the square root, but these two terms are identical, so principally the square root disappears, and you need just H0 minus magnetization. And it will be 2000 Ørsted minus 1750, it will be smaller than 1 gigahertz. So you see, you just took magnetic sample, you magnetize it, you change the orientation of field, and you strongly change the ferromagnetic resonance frequency. And in general, always keep in mind that if you want to work with thin film, magnetized perpendicular, first question, what is magnetization? Yeah, so you need to apply field which is larger than magnetization in this sample, if you want to magnetize it. If field will be smaller, magnetization will be in plane. It will never be magnetized out of plane. Good. Now let us take sphere. All the magnetization, so the same material, the same parameters, and x and y and z are the same for pi over 3, and we plug everything in, and we are coming to very interesting solution. Just pay attention. It's gamma H0. There is no magnetization at all because of this interesting contribution from demagnetization. So it means that if you will take a yttrium garnet sphere, or you will take a permalloy sphere, or any other sphere, frequency should be the same in the simplest case, and frequency will be 5.6 gigahertz, something in between, thin film in plane and out of plane magnetized. And then depending which, for cylinder, it will be another 2 frequencies and so on, but I don't go to cylinder because we usually don't work with them much. Okay. So much about Kittel formula. Other questions? Okay. No questions, then one important addition. Also, people sometimes are missing it. The point is that when you have real sample of real size, the precession, which we always consider to be circular, is not anymore circular. You will get ellipticity of precession. Moreover, if to make one step further, since a length of m should be conserved when it's precessing elliptically, this component projection to mz changes with double frequency. So we will consider it when we will discuss parametric pumping, for example. So it means that in reality, now due to the magnetization effect, everything changes, everything is getting more complicated. But first, what we need to take into account that we will get some, we can speak about polarization of magnetization. And this one is defined as my and mx, which earlier was simply 1. And now it's not anymore 1, now it's some parameter which depends on applied magnetic field H0, but also on all the demagnetization terms, and x and z, and y and z. This polarization can be coupled to ellipticity. So we work with ellipticity a lot, and by definition you can find it as 1 minus m minimal squared, absolute value squared, m maximal, absolute squared. And m maximal and minimum are the large and the small axis of the polarization ellipse. So it means that if your ellipse is precessing like there is some polarization, that mx is not equal my, you simply take the largest and the smallest part of this precession, like in an ellipse. So you will get ellipticity of precession. And again, you can define it just directly from Kittel formula without going further, that ny and x and y and z. Yeah, so there are all the magnetizing factors staying in there. And why it's important? Because it also changes damping. So if you will do all the routine we did, you can show that imaginary part of your relaxation of your frequency, which is your relaxation frequency. In the past, it was simply alpha omega 0. Okay, with this term alpha squared, yeah, which we discussed briefly, but pretty often it can be ignored. But here was simply resonance frequency. And now this resonance frequency depends on the N11, N22, and like it's shown here. Therefore, what we can conclude that lifetime depends on the ellipticity. And we really take it into account, not in all cases. Pretty often this contribution is small and can be ignored, but in some cases it does matter. Therefore, keep in mind that ellipticity should be carefully considered if you want to get omega relaxation in order to define lifetime of your magnets, for example. Other questions to Kittel?
If I have them symmetry, so the components of the demagnetization tensor are dependent on the structure, on the shape of my sample, right? And if I have a sample which is symmetric in x and y direction, this ratio is then again 1. So the ellipticity is again a circle.
Yeah. If you take a sphere, for example, yeah. So the question was if
the precession is symmetric.
Yeah. Yeah, correct. Yeah. So the question was, an answer was a comment that if you have symmetric systems, that these two components are identical, then ellipticity disappears and lifetime behaves like it should be. Mm-hmm. Yeah?
Is there a rule of thumb when we can consider the two surfaces to be infinitely separated? So when the component of the magnetization tends to 0, is there like in the millimeter range? Or?
So it's all about ratio. So you need to check ratio. Oh, it's hard for me to give you some value, but let's say if my width or length is 1,000 times larger than thickness, then I would already assume that we can ignore this demagnetization. And that's what usually happens. Our sample is, let's say, 1 by 1 centimeter, and thickness is 10 nanometers. No, but then it's the same. So the sum of the Mach will be the same. If you do it out of plane, you still say this 0, this 0, and this one collects all magnetization. So it's...
a big shift in the FMR frequency by magnetization.
Yeah, that's the most more or less limiting case, yeah? This one, when all the magnetization is the largest. Okay, and now we are coming to the last part of our this lecture. It's magnetocrystalline anisotropy. We are not going in depth, but we will try to understand how it works in general, and I will give you a few hints how to deal with it in a practical sense. In order to understand magnetocrystalline anisotropy, we need to understand what is spin-orbit interaction. For people who are watching it on YouTube, there is a advanced materials lecture where you can just check it in a bit more details. Here I will just briefly refresh what is it about. So the story is the following. If you have this Bohr model of atom, so electron is flying around the nucleus, like it's shown here, then magnetic properties are usually given by the spin of electron. But mechanical properties, for example, lattice, is usually coupled to the orbital motion, which is coupled, of course, to nucleus vibration, for example, like thermal phonons. And in general speaking, they not necessarily should be coupled at all. Therefore, but in reality they are, but physical phenomena which is staying behind the coupling is named spin-orbit interaction. So there is spin and orbit. This is very important phenomena which is staying behind many, many different properties. First of all, magnetocrystalline anisotropy, which we'll discuss here, damping, anisotropic magnetoresistance, I don't know, so magneto-optical effects, magnetostriction. So principally, majority of modern spintronics phenomena are in one or another way staying on top of spin-orbit interaction. The easiest way how you can describe spin-orbit interaction is presented here. What you do, you switch from the x, y, z coordinate system coupled to your nucleus. You are switching to the new system x, y, z small coupled to your electron. So more or less new coordinate system which rotates around the nucleus. This is just a little trick, because in this case, then your nucleus, which has z protons, is rotating around, and it creates a current loop, and it means there will be a magnetic field created inside, and the position of your electron, shown here, B, which is proportional to z to the power of 4, as it's shown here, and then your electron has spin. And as we discussed earlier, there is a magnetic moment, mu s, coupled to the spin, like it's shown here. And if you take magnetic moment and place it in magnetic field, of course, there will be some energy. And this energy is named spin-orbit interaction energy. And that's how it can be found. The simplest way to describe it, very important that here there's L product S, dot product. So it means that we need L to be non-zero in order to have spin-orbit interaction. Also, as you can see in this formula, z to the power 4, which means that spin-orbit interaction is usually more pronounced for heavy materials. And here A0 to the power of 3. A0, it's not Bohr radius, it's something different. It's just radius for different orbitals. And it also shows us this formula that spin-orbit interaction is more pronounced for inner orbitals, yeah, with smaller diameter. Good. Why is it important in terms of magnetocrystalline anisotropy? So what means magnetocrystalline anisotropy? Imagine that you have some sphere and you apply magnetic field and you measure ferromagnetic resonance frequency. And sphere is symmetric, so it means shape anisotropy doesn't work, doesn't matter how you rotate it, frequency will be the same. But when people take into a real sample and perform real measurements, they see that ferromagnetic resonance changes. Its frequency changes. And as a result, where it comes from? And it comes from the fact that there is a certain angle between applied magnetic field and some crystallographic axis. So it means we need to have a coupling between magnetic response and crystallography. And as we discussed, magnetic response, these arrows are given by spin of electron and orbital, so these orbitals are coupled to lattice itself. And strictly speaking, these arrows should not be in the middle because they don't show magnetic moment of the orbital motion. They show magnetic moment of spin. But idea is very simple. If we have spin-orbit interaction and if we apply magnetic field up, then that's what we have. And then, of course, it's very, very finger-like explanation. But if there is spin-orbit interaction, when we will apply field in another direction, we turn not only orientation of the spin of electrons, but also we will change position or orientation of orbitals very bit. And why it's critical? Because we discussed that exchange interaction of Heisenberg exchange interaction strongly depends on the overlap between the orbitals. Yeah? So electrons should jump from one to another. And it means when you change the overlap between orbitals, you will change exchange interaction. So it means that you will change magnetic properties. And as a result, you will have situations that magnetic response for one magnetization or for another magnetization will be different. So the turn of spins due to the spin-orbit interaction results in the change of the shapes of atomic electron shells. This leads to the attenuation of the exchange energy, which is a fraction of Coulomb energy as we discussed, the spin-dependent one. Okay, if we have this, then we will get again term hard and easy axis. By the way, in the previous case of shape anisotropy, I didn't discuss it, but we also have easy and hard axis. So easy axis means that when you magnetize it along this axis, the total energy is decreased. So it means that it's a comfortable, favorable orientation of magnetization for the system. So if you would take cylinder and you will apply magnetic fields, then you will have easy axis like this or like this. If you try to apply it like that, there is demagnetization, system is unhappy, so energy increases. And this will be not axis, but a hard plane in this direction. Yeah. So thin film always prefers to be magnetized inside, in plane, because this is easy plane then. If you take now sphere, where shape anisotropy cannot give us easy axis and hard axis, but there is crystallographic anisotropy, so there is magnetocrystalline anisotropy, we again will get hard axis and easy axis. So it means that again there are selected orientation of magnetization with respect to crystallography, with respect to axis of your crystal, when you can minimize or maximize energy of your system. How people describe this? According to Gurevich-Milkovich, an approach was proposed by Akulov, who said simply written down expression for energy of anisotropy in the form of power series M0 projections on crystal axis. So it means that principally there is no ab initio or whatever approach. There is just a general principle of symmetry. And he proposed to write empirically, more or less, projections of this M0 onto different crystallographic axes with different constants. So we don't know what is the physics stand behind it. We just later measure it in experiment, but we introduce this anisotropy constant, and this approach works perfectly. We can really describe our magnetization precession. For example, if you're speaking about rhombic structure, like it's shown here, then A, B, and C are equal, alpha, beta, gamma are equal but not equal 90 degrees. Then this energy of anisotropy can be written in the following way: K11 alpha 1 squared, K12 alpha 2 squared, plus some other terms. What is this alpha? It's a cosines of m with respect to symmetry axis. So we can find it as mj over divided by m. So you have such way how you can define your anisotropy in rhombic system. Often used so-called uniaxial anisotropy, which you define in the following way. So it can be not only uniaxial, but it can be trigonal, tetragonal, and hexagonal. But in some cases, you take into account that properties, this and this changes strongly. So this is my uniaxial anisotropy, and you ignore change in properties perpendicular to your axis of anisotropy. As a result, what will happen is that we can introduce only one angle theta, which is angle between your crystallographic axis and applied magnetic field, or magnetization. Yeah, and then you will get anisotropy can be defined in such form with higher order anisotropy terms. Very commonly used is cubic anisotropy. Yttrium has cubic anisotropy. Many other materials have cubic anisotropy. And in this case, we have K1, first anisotropy, K2, and you see it's a bit more complicated formulas, but all this is coming just based on the symmetry principle. So, of course, in cubic anisotropy, you need to have this 90-degree rotation symmetry, and so on. And if you will make your, and then these alphas, 1, 2, 3, these are cosines of m with respect to this axis. One, so you know all the similar indexes, 1, 0, 0, 0, 1, 0, 0, 0, 1. And, but in this case, one can make things simpler. You can pass from these three angles, cosines, simply to two angles, theta and phi, as it's shown here. So you just couple to the axis 1, 0, 0, and then this is phi is your axis in this direction, and this is theta is another angle. So more or less it defines angle between 1, 0, 0 and m0, but in such a way that you have two coordinates, two angles theta and phi. And then you can rewrite this anisotropy field like K1 and K2 like it's shown here. Okay, why it's important? Because it changes from magnetic resonance frequency in the simplest case, like it's shown here. You see the formula for ferromagnetic resonance, omega 0 squared over gamma squared, as a function of theta and phi. And you see that it's very bulky formula. So there is external field, there is HA1 and HA2 even ignored in this case. All these formulas with crystallographic anisotropy are bulky and complicated, but on the other hand side, there is nothing complicated. You just need to plug it in. But my message here is that frequency changes, and depending how you magnetize it, along which axis, the resonance frequency also is different, like it's shown here. Or for example, in Gurevich-Milkov, you can find this ferromagnetic resonance field, H resonance normalized by the anisotropy constant, you see that it depends on the angle and with this 90-degree symmetry, yeah? Like it's shown here. Okay, so that's a general issue, and now coming to the very practical case. If you work with thin film having cubic anisotropy, there is literature in this. You can find it, and there are more detailed, more clear papers and less detailed. We also made one, so I can recommend you this paper where Chris Levchenko has in Czech supplementary material where he invested some time, more or less, to take all this literature and to carefully sort it out. Mainly it's based on previous papers of Professor Zavislak. And here, at the end of the day, she defines a frequency for ferromagnetic resonance for in-plane magnetized sample thin film, for out-of-plane magnetized thin film. Here you see all these crystallographic constants depending how you magnetize it along which axis. And at the end of the day, you more or less have the 6 formulas for ferromagnetic resonance, which you can use. So here is taken into account. So by the way, there is different type of substrates, how yttrium iron garnet is grown. This is, for example, in gallium gadolinium garnet growing onto 111 substrate, and then it looks like this. These formulas have one form, and sometimes people grow with a GGG on 001 plane, then your crystallographic anisotropy looks like that. So here in this picture you can find all these angles, what is important, and then depending how your yttrium iron garnet was grown, or any other cubic material, yeah. So it's not only for YIG. And depending how you magnetize it along which axis. So here, of course, we take into account only main axis, yeah. So out of plane or along this axis or along this axis, because usually samples are cut properly with respect to crystallographic axis. Then the ferromagnetic resonance will be different. And in there you can find applied field, parallel or perpendicular to the plane. There will be cubic anisotropy. There will be uniaxial anisotropy, which is often taken into account, but also here is uniaxial anisotropy of second order is taken into account. So cubic anisotropy, so principally it's not only cubic, yeah? So we take into account here both uniaxial and cubic, and cubic is coming simply from the fact that YIG has cubic structure, like it's shown. But uniaxial anisotropy is pretty often coming from the fact that there is a lattice mismatch between material and substrate, or there is some other technological processes. So for example, your lattice slightly changes, gallium gadolinium garnet and YIG, then a crystal will be stretched, vice versa compressed very slightly, but this mechanical stress induces this uniaxial anisotropy, which in some structures can be very big, might be even much bigger than, often it's much bigger than cubic anisotropy, because yttrium iron garnet is a material with very small cubic anisotropy. It's one of the reasons why people like working with him, that it has very weak anisotropy. And when you work with 111 GGG substrate, then its role, if you can see here, this HC square is getting very small, so it means that its role is getting even smaller. So much about cubic anisotropy. Yes, please.
And can you give some numbers how big the shift can be in YIG due to the...
So if I can give you numbers how big the shift can be. So let's say cubic anisotropy, it's 42 Ørsted or something like this, from 40 to 50 Ørsted. And maximal, so here, as I said, it's specially growing in a way to minimize its influence, that if you work with sphere, where there is only cubic anisotropy, that FMR frequency change is the smallest. But maximal what it can be, if you simply multiply it with ferromagnetic ratio 2.8 megahertz per Ørsted. If you take, let's say, 50 Ørsted, multiply it with 3, then you will get 150 megahertz shift. this is maximal which you can achieve, but in reality I would say it's not more than a few tenths of megahertz. But it all depends at which field, and yeah, so one need to perform more careful analysis.
And it's also vary in one wafer, for example, itself.
If there is,
It can change from, let's say, an outside part of the wafer to the inside.
so the question is if we can expect change in crystallographic anisotropy or so, depending in which part of the wafer. The answer yes, we can expect. The point is that if you take, especially if you do liquid phase epitaxy, also thickness pretty often changes. It's thicker at the edges and thinner, so therefore thickness is different. There can be some contamination. There might be simply this liquid, melted material from which you grow YIG might be not uniform. Maybe some other factors, which I'm not a material scientist in the sense, so for me it's hard to answer. But from practice, yes, we always trying to characterize. So when there is 3-inch wafer, you cut it into samples. We always trying to pre-characterize concrete this sample before we go to more complicated experiments, because it might be that really sample from one and other part have slightly different properties. No more questions? Other more questions? If there are no more questions, then thank you very much for your attention.